Hello and welcome to a new video. This is for Precalculus / trigonometry, going through Math UC, doing lesson 9 this time, which is about proving trig identities. So this is going to be quite a ride. This is generally considered to be one of the toughest parts of a Precalculus / trigonometry class because we are proving, which people don't like to do, and it definitely is something that takes practice to be able to get the hang of what to look for. It's going to be similar to actually what we did in lesson 8, but we are adding some new identities to use, and it's going to be a fun time. I recommend that you click the link in the description to go to my website and get a free notes page to use to download and take notes on. Also, having an identity sheet that tells you what the possible identities that you can use are can be super helpful, especially at the start here for figuring these out. If you're doing like an AP pre-calculus class, it's not AP, pre-AP pre-calculus class, it's super likely that your teacher will want you to have these identities memorized, but at least while you're practicing, having them there to look at can be super helpful. So let's get started. Let's talk about some new trig identities. So we talked about quite a few last time, but these next ones are, I think, really cool, but require us thinking, or it's helpful to think of the unit circle as we're talking about where they come from. So I actually have like the first quadrant here set up so that we can look at the first quadrant of the unit circle. If we think about the unit circle, if you don't know what the unit circle is, I'll try to put a link in the description to a video about the unit circle for you so that you can go look. The unit circle is basically we normally have a full circle, not just a fourth of it, but we have this idea that these angles that we're going out to here are going to be at points, right? And it's a unit circle, so we make the hypotenuse be 1 and then let that affect what our sides are. This is a 45-degree angle, so our sides end up being square root of 2 over 2 and square root of 2 over 2. So what we do is we label this point square root of 2 over 2, comma square root of 2 over 2. And what we can do is we can memorize this or have one handy and say, okay, anytime I need cosine of 45, I look at the x value because this is the adjacent side here is what's going along x. So this point is the cosine of 45. And then is the sine of 45, that's our y value, because this would be our opposite side. So sine of 45. And just in general for the unit circle, for each of these points that we could have, we can generalize this to say, okay, my x value for these points is giving me cosine of whatever the angle is. My y value is giving me sine of whatever the angle is. So we can generalize these points to be cosine theta, comma sine theta. But we can actually kind of further then take this and say, okay, well that means that, all right, so for a generic kind of triangle here, let's pretend like it's not necessarily 45 this time. For this generic triangle theta, we could label the x side of this as cosine theta, because the hypotenuse is 1. We label this side as sine theta, and then these are called, what we're doing new today is called the Pythagorean identities. So let's think about what the Pythagorean theorem could tell us about this. The Pythagorean theorem says leg squared plus leg squared equals hypotenuse squared. Well, if one of the legs is cosine, then we could write cosine squared. Remember, we put the squared between the s and the theta. And then we could say our other leg squared is sine squared, and that has to equal the hypotenuse squared. The hypotenuse is 1, so that gives us 1 squared. So what that means is cosine squared theta plus sine squared theta equals 1. This is a super important identity, I guess, just for the fact that if you can make something end up being cosine squared plus sine squared, you can exchange it with 1, which is so much simpler than having cosine squared plus sine squared. So that's why this is helpful. There's 2 other Pythagorean identities that involve the other trig functions. We get those basically just by going through and dividing the whole identity by something. So there's this weird kind of thing where when we're proving identities, we're not allowed to move things around, but these identities, we can move things around. So to get the other identities, I have to think about what would happen if I, divide all of this by cosine squared. How would that change this? Now, that's not normally something we're allowed to do if we were proving an identity, but it is something that you have to kind of do to get this. Maybe you don't have to do it. This is one way to get these other identities. Cosine squared divided by cosine squared would be 1. Sine squared over cosine squared would be tangent. And then 1 divided by cosine squared, we can use the reciprocal of cosine, which is secant, and get secant squared. To figure out the other identity, because there's 3 of these Pythagorean identities, instead of dividing by cosine, we'd divide by sine squared, and get sine squared theta, sine squared theta, sine squared theta. So cosine over sine is cotangent, so this one would be cotangent squared. Sine squared over sine squared, those are the same, so they cancel but give us 1. And then 1 over sine is equal to cosecant, so this would be cosecant squared. So here's our 3 Pythagorean identities written how they normally are once I erase this. And so what is going to be helpful here for us is that is knowing that you can't just square root these for a lot of reasons. But even if you decided it's okay to square root these for some reason, square rooting these doesn't actually simplify the way you might think it does. If I try to square root this, it doesn't actually simplify because of the plus in the middle. If it was multiplication in the middle, yes, I could simplify that, but it's not. So we cannot take the squareds out of these. Like our other identities that we did last time, we were able to introduce squareds in. You can't take squareds out, though, of ones that start off squared. What we can do, though, is we can actually manipulate these to get basically equivalent statements. Like if cosine squared plus sine squared equals 1, that means I could also think about, well, what if I had cosine squared by itself? What would that look like? That would be cosine squared equals, I'd have to subtract sine squared over so that I get 1 minus sine squared. That's part of what makes these tricky, is that it's not necessarily that you're going to see cosine squared plus sine squared, which you might, but you might instead see 1 minus sine squared and be expected to change that to cosine squared. So that's something we want to think about is, okay, how could we, if we see a squared somewhere, is it helpful to try to use the Pythagorean identities to change it to the other trig function? And sometimes it will be helpful, sometimes it won't. Here's the Pythagorean identities written out. Like I said, this is how they're typically written, but we can rearrange them to form other identities by subtracting things over to the other side. Proving statements that are true. Most of this is the same as last lesson, but I added 5 and 6. So I will point out 4 says, don't move things across the equal sign. When we're proving, we're not allowed to do that. Okay, when we are trying to say these 2 things are equal, we need to work with one side or the other, but not have those sides interact. I know it's kind of a weird thing since we're allowed to do it with the Pythagorean identities to get something that's equivalent, but don't do it while you're proving. 5 says try getting common denominators if you have more than one fraction, which can be a little tricky to wrap your head around whenever you've got sines and cosines and things like that in your denominator, but that is one of our key strategies. And then 6, this is new because of the Pythagorean identities. Do we have a trig function squared? Would it help to use a Pythagorean identity to change it? The way you know it would help is if, it right away makes things simpler, like you're able to do 1 plus tangent squared and change it to secant squared, that's simpler. Or if you realize, hey, I have sines and cosines. What if I use the Pythagorean identities to make it to where everything I have is cosines or everything I have is sines? So hopefully we'll see these in action. I have quite a few examples here. Basically, to get good at proving trig identities, you have to practice, and you have to practice in such a way that you know what the right answer is, or you have someone to ask questions of. So it's going to be really important that you Practice, practice, practice. And if you keep getting help on problems and aren't able to do them on your own, that just means you're not done practicing. Hopefully you get to a point where you can do these with minimal to no help, because there's really only so many like situations out there. There's not infinitely many problems or types of problems that we can be asked to do with these. So we just need to be able to do a ton of practice, and to be able to ask questions when we get stuck. So let's check it out. Example 1. So all of these, I believe, say prove that each of the following equations is an identity. What that means is just an identity is a statement that's true. So let's prove that this is really true, that we could do secant theta plus 1 over secant theta minus 1. That is equal to 1 plus cosine theta over 1 minus cosine theta. You may be thinking, hey, won't we be using the Pythagorean identities on all of these since that's our new identities? And you would be thinking wrong. It does not necessarily, like, we are not going to use those identities on every single problem. It's just as likely, if not more likely, that we'll be using our reciprocal identities on these, so just keep that in mind. This one is a little tricky because basically we have to think these are reciprocals of each other. So how do I change one of them to the other? And so we could kind of think of it this way. Secant theta is 1 over cosine theta, right? So we could kind of make this change. Sometimes as we go through this, we make things look worse before they get better. Kind of like whenever I try to organize my stuff, I tend to make it look worse before it looks better. But here's the deal. If we look at it this way, it might make it more obvious that what would be really nice is if we could multiply both of the things on top and both of the things on bottom by cosine theta. Because if we can do that, if we can multiply this by cosine theta over 1 and distribute, what happens here is that it cancels out in this first one, and then it just turns the plus 1 into cosine, which is what we want on top, right? We want 1 plus cosine. But in order for us to be able to do that, and it's good that this is how it works, we actually have to multiply by cosine theta on top and cosine theta on bottom. Now, like I said, that's convenient because that's what we needed to do to the bottom as well. But multiplying by cosine theta over cosine theta is the same as multiplying by 1. It's just like whenever you are dealing with fractions and you multiply something by 2 over 2. And you're allowed to do that because 2 over 2 is just 1. It's an equivalent fraction. Okay, so that's why we're allowed to do cosine over cosine here. And what it does is it turns this into 1 plus cosine theta on top and turns it into, let's see, the cosine thetas would cancel here, and then we'd get minus cosine theta, so 1 minus cosine theta. And actually, it was pretty quick to get here. It was knowing what to do. That was kind of the issue for this one. That's a little bit tricky. But now, hopefully, if you see a problem similar to this, you'll go, what would happen if I multiply it by its reciprocal, basically? It would change things so that instead of having secant, we had cosine. Instead of having 1, instead of having secant, we had 1. Instead of having 1, we had cosine, which is what we needed to change it to. So that's example 1. Example 2. We've got parentheses here, and we've got cosecant and cotangent together. Now, sometimes it will be true that multiplying here is a good idea. Sometimes it's not true that multiplying is a good idea, but you got to start somewhere. So if you're looking at this and going, I don't know what to do, our options are change everything to sines and cosines. It's not a horrible idea, but it isn't something that's actually strictly necessary to get this problem right, so let's hold off on that. Let's FOIL these out. Let's multiply. And if it's been a while since you've FOILed, I get it. What we're going to do is first times first. So cosecant x times cosecant x. That's the same as when we have x times x and get x squared. But instead of having x times x, we have cosecant times cosecant. So we get cosecant squared. That's first. Then we're going to do our outer terms. Cosecant x minus cotangent x is minus cosecant x cotangent x. That's the same as doing x times negative y, right? That gives us negative xy. Then we've got inner, so cotangent x times cosecant x again. Those just are going to go next to each other. And then we've got last, so cotangent x times negative cotangent x, which would be negative cotangent squared x. Now, a couple things are going to happen to us. First, these middle terms, and it may not be obvious to you initially, but these are actually the same thing but with different signs. One has cosecant cotangent, one has cotangent cosecant. Multiplication can be switched around if it's just multiplication. So I wrote it with cotangent first, but I could have written this with cosecant first, like this. Then it's even more obvious, right, that these are like terms. So if I have a -1 and a +1, they cancel each other out. And that leaves me with cosecant squared x minus cotangent squared x equals 1. So now we can look at our identity sheet again. The fact that this equals 1 should kind of be sending some alarm bells our way because we have a Pythagorean identity that says, what does it say? 1 plus cotangent squared equals cosecant squared, I think is what it says. And so basically what we can do is we can say, well, what would happen if I wanted it to be 1 equals something, right? Since this is 1 equals something. Well, to do that, I'd have to subtract the cotangent squared over here. And that means that I'd have 1 equals cosecant squared x minus cotangent squared x. That's what we have, right? So I can say, all right, cosecant squared x minus cotangent squared x, that is 1. So I get 1 equals 1, and now I'm done. That was the proof. So there was kind of two parts to this, like understanding the algebra involved with foiling trig functions, when we combine them to be squareds and when we just put them next to each other. But then there was also recognizing that there was an identity hidden here. It's because it wasn't the exact same. It was a little bit different. The other way, by the way, to do that, where you don't have to think about rearranging the identity yourself, is to say that identity tells me that cosecant squared equals 1 plus cotangent squared. So we can replace the cosecant squared with 1 plus cotangent squared. This actually might be way easier to think of now that I think about it. That would mean these would cancel and we'd still end up with 1 equals 1. So that's another way of doing it. In case you didn't realize, there are more than one way to do most of these problems. There might be a quickest way or an easiest way. Those are kind of subjective though, at least easiest way is subjective. So keep that in mind as you're going along, that you might do it differently than the person sitting next to you, but that's possibly okay as long as you're using the correct like algebra rules and identities and things like that. Let's look at this one. So I think that distributing or foiling here would be a good idea. So we'll do 1 times 1, which is 1. Then we'll do 1 times negative cosine x, which is negative cosine x. Cosine x times 1, which is plus cosine x. Cosine x times negative cosine x, which is negative cosine squared x. So that means our middle terms cancel out and I have 1 minus cosine squared x. So hard to see if that was necessarily helpful. In fact, it might actually be helpful for us to think about the other side now, because tangent squared is sine squared over cosine squared using our quotient identities. And that's helpful because I can cancel out these cosine squareds and get sine squared. I am allowed to work on either side of the equation. I'm just not really supposed to change them like at the same time. So this was helpful because hopefully you can pretty quickly say, oh wait, there's a Pythagorean identity that helps me with this. 1 minus cosine squared equals sine squared. Because I can rearrange this identity so that it looks like what I have. I can subtract the cosine squared over to the other side so that I can make this exchange. This is sine squared equals sine squared. Or alternatively, if we don't want to, I don't need to circle that, that's not actually my answer. The whole thing is my answer. Remember that proving, you already know what you're trying to get to, so the the work you're doing, that you're showing how to get there is really what your answer is. Alternatively, we could have said, okay, I know that 1 equals cosine squared plus sine squared, so let me put that in, and then we would have subtracted cosine squared and still ended up with sine squared. So that's how that goes. Whew, let's look at this one. This is long. We've got a bunch of squareds, but they equal 3. So what's interesting about this is it kind of seems like, well, maybe we're going to find some Pythagorean identities hidden in here. In fact, at the beginning, sine squared plus cosine squared equals 1, right? It doesn't matter that sine squared was first, because we could just rearrange this so that cosine squared is first. But this part is 1. What else can we do, though? We have tangent squared and secant squared, cosecant squared and cotangent squared. So look at those identities and think about what order maybe would be helpful for us to have this. I'm going to think about secant squared minus tangent squared and check that based on my identities. And I'm going to check it with cosecant squared and cotangent squared and see if that also is an identity, which it is. This together equals 1. Or if you'd rather think of it as, I'm going to replace this with 1 plus tangent squared, because that's how my identity looks. It has secant squared equals this. That's also an option. Either way, this all cancels and gives us 1 as well. Same thing happens here. This together is a Pythagorean identity and equals 1. So 1 plus 1 plus 1 is 3. 3 equals 3. Voila. So this was just basically us having to pick out and recognize that we had those Pythagorean identities. This is our last example for this video. I may do some more identities at some point, or try to like link to, if I probably have another video with identities, because like I said, it basically takes you doing enough of these to start to see the pattern emerging. And so if you haven't done a ton, well, that's gonna make this difficult. This is actually a problem that may be in your workbook, I think, because I looked at this, I was like, this is tricky. I think that we should do it together. So let me think. How do I want to start this out? Because there's lots of things I could change, but we want to change like the right thing. So just as a side note here, on the right side, 1 minus sine theta over sine theta minus 1, we can't cancel those out, except that if we had different signs, it would work, right? When we have things like 1 plus x over 1 plus x, we can cancel them because they're the exact same. When we have 1 minus x over x minus 1, we can't cancel those because they're not the same thing. But we could take a negative out of one of them using factoring, and then all of a sudden they are the same. Okay, so keep that in mind as I suggest to you that maybe the best thing to do is to actually simplify over here on the right side and say, it doesn't matter which one of the two we do it to, but if I say, okay, I want to take a negative 1 out of the top, that would make this negative 1 plus sine theta or sine theta minus 1. And that's going to let me cancel out the sine theta minus 1s. That goes and that goes. That's helpful because now I have negative 1 over cosine theta. The negative part doesn't really matter. 1 over cosine theta, I can switch to secant theta. So this equals negative secant theta. Now I'm going to be honest, I do not yet know how we're going to get to negative secant theta. But boy, does this look a lot simpler to try to have as a goal. So let's think. Whew, okay, I'm going to start my work up here so that I have room. I look at this and I go, okay, I can change these to, actually let me go back a step. I can change these to all be in terms of sine and cosine, and it's quite possible that I will find that to be helpful. By the way, Pythagorean identities here I don't think are going to be helpful because nothing so far has been squared. It may be that we'll end up with something squared, but that's not happening yet, so you would not want to use a Pythagorean identity. I'm going to change everything on the left to being in terms of cosine and sine. So cotangent, using our quotient identities, is cosine over sine. And then cosecant is 1 over sine. And tangent is sine over cosine. Remember, our goal is we're getting to negative secant theta. There's definitely more than one way to do this problem, by the way. I'm going to come over here and get a common denominator on the bottom because I have 1 over sine, which is a fraction. I have a fraction over a fraction. So I think if I make there be a single fraction on bottom, that will be helpful. So to make a common denominator with 1 over sine, I need to times this by sine over sine. Okay, so that means I have sine theta minus 1 over sine theta. That's the bottom. On top, I have cosine theta over sine. Now, why is that helpful? When I divide fractions, I flip the bottom fraction and multiply. So this is really cosine theta over sine theta times sine theta over sine theta minus 1. So those signs cancel, and we get just cosine theta over sine theta minus 1. And we are still plus tangent theta, or sine theta over cosine theta, this whole way through. I'm a little worried because this actually looks a lot like, or similar to what we had before. So I'm worried that maybe changing to secant theta was not as helpful as I thought it was going to be. So what do we have left that we can try to do? Could we get a common denominator here and see if that's helpful? I think that's what is helpful here, even if it doesn't feel very nice to do it. Because if I get a common denominator, I'm also running out of room. If I get a common denominator, that means that this fraction needs cosine on bottom, and this one needs sine theta minus 1 on bottom. Okay, so I'll just, I guess, erase this and start working over here. All right, so this gives us cosine times cosine, which is cosine squared. And this gives us, we could distribute this and get sine squared and minus sine theta. Yeah, I'm definitely regretting the changes we made earlier. This is cosine theta times sine theta minus 1. Okay, check out how close we are to the original right side. So yeah, like if it were me, I would go back and like erase what we did to the right side because we didn't really need to do it. So cosine theta times sine theta minus 1 is right here. Cosine squared plus sine squared, our Pythagorean identities did show up here, okay? So this would be 1 minus sine theta, which is what we were going for, over cosine theta times sine theta minus 1. Like I said, this one was complicated, especially because like there were a lot of different directions we could go. It was hard to know what was the right way to do it. In fact, you'll notice I'm going to leave this in. I did not pick the best way to do it at first. So that's why we got to practice. We got to, work together to try to come up with answers when we can't get them on our own, and then just try to get better as we go along. Thanks for watching. I hope you'll subscribe, leave me a comment if you want to, and I will see you in the next video. Bye.